Moving into section 10.4, what we're going to learn now is how to divide radicals. So very similarly to the multiplication, notice that the definition requires for division to be defined totally, right? The index in the numerator has to match the index down in the denominator. When we have that condition, just like multiplication, we can put it all underneath one radical and then basically divide radicand by radicand. So very, very similar to multiplication. As a matter of fact, if we think in terms of our exponential rules, this side becomes a over b to the 1 over n power. And of course, the exponential rule, we have a power of a quotient. We can break that up and apply the numerator to that power and the denominator to that power. So as soon as I apply that exponential rule, I have this side. So there's basically your proof. It comes down to our ability to raise a quotient to a power, which is just basically distributing the powers. What I also want to call to attention earlier, I think it was a 10.2 or somewhere in there, we do have problems if we have something like the cube root of x divided by the fourth root of x. Notice that the indices are not the same, so this does not apply. What we did back then is we converted them to their fractional exponent parts, and then we used the quotient rule to subtract our fraction. So be careful. We can still divide when they're not the same. We just have to use another rule. But if my indices are the same, it's as simple as just putting it together and then simplifying the fraction and moving forward, as you will see me do here in a moment. So let's practice this definition. The first example I have is we're dividing the square root of 27 by the square root of 3. So my definition is satisfied. My radicals are the same. So I can rewrite this. I can put it all underneath one square root and take my radicand and divide it by the radicand. Of course, now that I have a nice neat fraction, 27 divided by 3 is 9, and of course we know that the square root of 9 is 3 using our principal square root. So that worked out very advantageous for us. Right now, hard to simplify that. The square root of 3 is not even a nice number. The square root of 27 is not a nice number, but by going through the process of division, we were able to create a nice number and then get rid of the radical. So in a sense, we simplified. Same thing here. We have another division. Again, kind of hard to simplify the top. We could do some things to the bottom, but before we do that, right, I do see that my radicals are the same index. So I can keep this all underneath one cubed root and then take my radicand and divide it by a radicand. And now we're basically down to simplifying a fraction. I think 2 goes into 16 8 times, right? So we have a 1 over 8, and then x and x to the fourth. Basically, there's 4 x's down here. They'll divide out with 1, right? So x divided by an x. So we're left with x cubed down there. So we have the cubed root of 1 over 8x cubed. And of course, now what I'm going to do is go back in reverse here, and we can rewrite this as the cube root of 1 and the cube root of 8x cubed. And that top is 1, the cube root of 8 is 2, and the cube root of x cubed, well, there's my power matches my index, so it's gone. So that also is able to be simplified. So notice in that example, not only, I kind of used this rule twice. Once to put it together, and then after I put it together and simplified it, I was able to break it back apart and continue to simplify. And that'll be important at the end of this chapter, but getting used to the concept of simplifying. Next example looks like a train wreck. It is a train wreck, but the good news is my radicals match up. So we can put this all underneath one gigantic radical, and we have this radicand divided by this radicand. And so if we simplify this fraction, we still have another fourth root. 100 divided by 25, well, that's going to leave us with 4, right? 25 goes into once and 4 times. Using our quotient rule, 10 take away 2 is 8, so we have x to the 8th. And then y to the 7th, y to the 4th, this becomes y to the 3rd. And so everything basically divided out. So let me rewrite this. We're talking about the fourth root of 4 x to the 8th and y cubed. Okay, so there's our division. Of course, now we simplify. We've seen that we don't want any powers higher than the index. So, technically speaking, again, shortcut, 4 goes into 8 twice, or we can take that x to the 8th and break it up into powers that match the index. So I have an x to the 4th, I have an x to the 4th. So I have an x squared coming out. 4 is not a nice fourth root, and y cubed already satisfies the fact that the power is less than the index. So don't forget to simplify your radicals. So we started by using our division rule, right? Simplified the fraction that I had, and then simplified the radical that I had left. And so that's as simple as we're going to get. That's probably going to be your answer in the back of the book for something that crazy. All right, and then the last example, the one thing I want you to note about it is that I've got this extra 8 floating around. So be careful, right? Because what we're dividing here is what the radicand under a radicand. So quite frankly, if you need to, we're talking about the fraction 1/8 multiplied to the fraction 32 x to the 5th y to the 7th square root of 2xy. So that's really what's going on here. This would be another way to write that, and that fraction right there is the one that we can actually use our rule on. So be careful of wandering coefficients, if you would. So working on this 1/8 is along for the ride. I can put this all underneath one radical. We get 32 x to the 5th y to the 7th 2xy. Simplifying this radical, all right, we get 2 goes into 32 16 times. We have 5 minus 1, that would give us x to the 4th, and 7 minus 1 would give us y to the 6th. So let me rewrite that so it looks a little cleaner. So we're basically talking about the square root of 16, x to the 4th, and y to the 6th. So there's the division, and then now what we have to do is to continue to simplify. And so when I simplify this, again, I like to use the shortcut. 2 goes, square root of 16 is definitely a 4, right? 2 goes into 4 twice, so I know there'll be an x squared. 2 goes into 6 3 times, so I know there'll be a y cubed. And this is still being multiplied by 1/8. If you don't like that, again, as we saw, we have the square root of 16. This is x squared, y squared, y squared, y squared. And we know the square root of 16 is 4. There's a power that matches the index, another power, so we have x squared. Here's a power that matches the index, here's a power that matches the index, here's a power that matches the index, so we have y cubed. 1/8 and 4, right, treating that as a fraction. 4 goes itself once and there twice. So our final answer for this would be x squared, y cubed, all divided by 2. And so, so very nice in terms of using the definition to get it started. We simplify a fraction like we learned how many moons ago, many weeks ago, and then we make sure that our radical is simplified. One of our big rules right now is that no powers are higher than the index. So I had to use it here, and I had to use it there to kind of continue to simplify. So there's your beginning, much more coming.